Yeah, so good evening all of you. So please type in the chat box, am I audible to you, and can you all see the screen clearly? So please type in the chat box, can you all see the screen clearly, and can you hear me? Yeah, audible and visible, good. So now if you quickly recall yesterday's session, we have started linear algebra, and in yesterday's class we have seen all the basic definitions of matrix algebra, correct? We have defined what is a matrix, and of course we have seen what are different kinds of matrices depending upon the type of element situated in that, correct? And we have also seen few properties of matrices, like matrix multiplication we have seen, and we have seen matrix multiplication need not be commutative and all these things. So if someone is new for today's class, definitely I would like to recall things quickly for you. Just a second. Yeah, better. So we have seen basically types of matrices. So we have seen square matrix where m is equal to n. So this is a square matrix we have seen, and of course let me reduce this a bit. Okay, fine. So we have seen a symmetric matrix where A transpose is equal to A, and also if this is symmetric matrix, then we have also seen A transpose is equal to minus A as skew symmetric matrix, and of course we have seen what is an orthogonal matrix as well, correct? So orthogonal matrix is nothing but A times of A transpose is same as A transpose into A is equal to I. This is orthogonal matrix, correct? So after defining these types of matrices, we have stated something special matrices like idempotent matrix, idempotent matrix, where we have seen this A square is same as A, and of course in involutive matrix we have seen A square is equal to I, correct? This is what we have seen. Yeah, good evening all of you. So please try to focus here. So and also we have seen some matrix of special type which is called the nilpotent matrix, where of course even if we have a non-zero matrix A, then there exists some positive integer n such that A power n is equal to 0, even though if A is not equal to 0, and the least value of n possible, least value of n that satisfies A power n is equal to 0, that satisfies A power n is equal to 0 is called, can you tell me what is this n called? What is the least value of n which satisfies this A power n is equal to 0 called? Can anyone tell me what could be this value? It's nothing but index of this nilpotent matrix. So we have seen all these things. I am just going through the things quickly so that if someone is not present for yesterday's class, you will be getting the things in a short way. Okay. So of course, and also we have seen few properties of matrix multiplication, like matrix multiplication need not be commutative. Then we have seen matrix multiplication is both associative as well as distributive and all these things. And of course later that we have seen whenever some combinations are given, means if A transpose is equal to A and B transpose is also is equal to B, then AB plus BA is always symmetric, We have seen why these results are coming, correct? It's always symmetric, and of course we have also seen this AB minus BA is skew symmetric. So in general, if you have any combination of this A and B, we have seen how to identify the symmetricness or skew symmetricness of the matrix, correct? We have seen all these things, and then we moved on to something like any square matrix can be written as a sum of a symmetric matrix and a sum of a skew symmetric matrix, correct? We have seen this, and we have very good results to show this matrix is a symmetric matrix, and of course this matrix here is a skew symmetric matrix. We have seen all these things in yesterday's class. I am just writing the things again so that you can recall. Skew symmetric matrix, correct? We have seen this. Can you all recall all these things till this moment? We have seen all these things in yesterday's class. So can you all recall things till this moment? And once we have stated this, we started solving few good number of problems on this, and then we ended the lecture, correct? So in today's class, straight away we will go for some problems from yesterday's basics, and then we will discuss something new. Okay. So now this is the first problem straight away I am giving you. It's a question from 2020 mechanical engineering. So please try to solve this. I will be moving aside. So please try to solve this question. A matrix P is decomposed into its symmetric part S and skew symmetric part V. If S is this particular matrix and V is this, then the matrix P is dash, which is out of these 4 options. Yeah, good evening all of you. So please try to cope up with the things. So here they have given, they have decomposed this matrix P into a symmetric matrix S and a skew symmetric matrix V, and they have given both these parts and they are asking you what is the matrix P. Any one of you? What's the answer? It's B. Is it B? That's what many of you are telling. Is it B? Okay, look, we have seen any square matrix can be decomposed as a symmetric matrix plus a skew symmetric matrix, correct? We have seen this, and here it's given as per this decomposition, your P, which is a square matrix, can be decomposed as S plus V, because S is the symmetric part and V is the skew symmetric part. So if S and V are given to you, you can calculate P very easily, and of course P is nothing but S plus V, correct? We have seen this result, correct? In yesterday's class we have seen any square matrix can be decomposed as sum of a square symmetric matrix and sum of a skew symmetric matrix. So now if you apply this logic, this S plus V should be equal to P. Now in examination there is no need for you to add the 2 matrices completely. Okay, look how to identify the answer. -4 plus 0 should be equal to -4, correct? So the first element in this matrix P, so this matrix P is a 3 by 3 matrix, so the first column element of this matrix P is nothing but sum of this -4 and sum of this 0. So -4 plus 0 should be -4. If you check the options, we don't have a -4 here, and also we don't have a -4 here, it's +4, correct? So this is what we have. Next, if you check the second element, this is 4 and this is -2, so 4 plus -2 will give you a 2, which is present only here but not here. So this is the wrong answer, but B is the correct answer. Okay, so can you all understand how the answer for this matrix is option B? And of course it's an easy question and directly a question from our notes, so definitely we can solve. So can I go for the next problem? Yeah, answer is B, Suhas and Umesh. So we are going for the next problem. So please try to calculate this. If A and B are real symmetric matrices, so it's given A and B are real symmetric matrices of order n, okay, they should be square matrices of course. Which of the following is true? A and B are symmetric matrices. Symmetric matrices. Which is always true? We have seen this is a property of the transpose, correct? If A is equal to A inverse, then what's the matrix? You can clearly see A square is equal to I. Of course, A into A transpose is equal to I. This stands for orthogonal, and we are not sure about this always, correct? Matrix in multiplication may not commute, so definitely one thing that always happens is this AB whole transpose is nothing but B transpose into A transpose. We have seen in properties of transpose of a matrix. Next, so please try to solve this. In A and B are 2 matrices, and if AB exists, then BA exists when one of these 4 options should happen. What's the correct option? So please try to tell me here. What's the correct option now? All of you. So please tell me what's the correct answer. Option D, and few of you are telling option A. Look, if BA has to exist, if the order of B is m by n and if this is p by q, it's already given AB is existing. So if AB is existing already, so if this is of order p by q and if this is of order m by n, then definitely this q should be same as this m, correct? And similarly for BA to exist, this n should be same as this p, correct? So if BA has to exist, this n is equal to p, means number of rows in A should be same as number of columns in B. So only if A has many rows as B has columns, correct? Only if both A and B are square matrices, okay, even though it exists, but of course this sentence also implies this thing again. Okay, fine. So let's go for the next problem. 1998, a very old, generally number of questions on basic chapters are very limited, so that's why we will be going to very old years. so that to have some questions at least. Okay. So please try to solve this. A is a real square matrix, then A transpose into A or A into A transpose is always symmetric or skew symmetric, sometimes symmetric. So please try to answer this. And of course, if you are liking the contents, please like the videos and of course share them among your circles. Okay. So option B, option A, option D, option B. Okay. Look, whenever they give you some combination like this, I always asked you to treat this combination as a single matrix, correct? So let us suppose C is equal to A times of A transpose. Now here options are something about the symmetricness of this matrix. So let's check about the symmetricness of this matrix, and for checking the symmetricness, let us calculate the C transpose. If you calculate C transpose, this is A into A transpose whole transpose. This is what you have. So this implies C transpose is equal to, look, if A is one matrix and if you treat A transpose as a separate matrix, then the transpose of this multiplication of matrices is nothing but, look, just in the previous question we have seen AB whole transpose is equal to B transpose into A transpose. This is what we have seen, correct? So if that's the case, then this matrix can be written as A transpose whole transpose into A transpose. And of course, you know, if you if you transpose any matrix even number of times, the resultant is the given matrix again. So C transpose is equal to A times of A transpose, and this is nothing but C, correct? Because you have taken this A into A transpose as C, so definitely this A into A transpose here can be taken as C. So C transpose is C, which means this matrix C is always symmetric, because we didn't substitute any specialized conditions here, correct? So definitely this C is always symmetric. C is always symmetric. Okay, so in examination, if some questions were given something like this, in yesterday's class also we have seen, if they give you some combination of matrices and if they are asking you about symmetricity or skew symmetricness of the matrices, then definitely this is the standard working procedure that you can follow. Is that clear to all of you? So shall we go for the next problem? All of you? Yeah, B is the correct answer. So shall we go for the next problem? I am happy that all of you have answered it correctly. Next, a question from 2011, of course. Now, so please try to solve this question. A is a square matrix which is neither symmetric nor skew symmetric, okay, and A transpose is, of course, this denotion is the transpose of this matrix. The sum and difference of these matrices are defined as S is equal to A plus A transpose and D is equal to A minus A transpose respectively. Which of the following statements is true? Can you tell something about this? So as you are asking minus A times of A transpose, look, that will also be a symmetric matrix, because all of you please try to solve this question. You pause your screen for a while and try to solve this. Meanwhile, our friends are having some doubts. So see here, you are talking about this matrix. So in yesterday's class, if you remember, I gave you one property, K times of any matrix whole transpose is nothing but K times of A transpose. Can you recall this? If you can recall that, then this can be written as, if you treat this as C, then C transpose can be written as minus 1 into A times of A transpose whole transpose. So this minus 1 can be taken out of the transpose because you can't transpose any scalars. So A into A transpose whole transpose. This is same as minus 1 into A transpose whole transpose into A transpose. So this is minus 1 into A transpose, and which is same as C again, correct? So you can see C transpose is again C, and this matrix is also a symmetric matrix. Okay. Meanwhile, what's the story for this? Option D. That's what many of you are telling. Okay, let me check. So now we know any matrix A can be written as sum of a symmetric part and a skew symmetric part, correct? And the sum of symmetric part is written something like this, and the skew symmetric part is written something like this, A minus A transpose. Now it's undoubtedly clear. In yesterday's class we have seen that this term half times of A minus A transpose is symmetric, and of course we have also seen this half times of A minus A transpose is skew symmetric, correct? So we have seen this. So if you know this, then definitely got it. Okay. So now if you get this, whenever this matrix is a scalar, is symmetric, then definitely there is no involvement of this, means there is no impact of this constant on the nature of this matrix, correct? If suppose if A is symmetric, then definitely 2A, 3A or any times some scalar multiplication of A is also symmetric, correct? Can you all understand this? Whenever if A is symmetric, then definitely K times of A is also symmetric. Yes? Can you all understand this? Yes. So if that's the case, then definitely this A plus A transpose means this S is symmetric. This S which is given by A plus A transpose is symmetric, and this given by A minus A transpose is skew symmetric. So both S and D are symmetric. No. Both S and D are skew symmetric. No, false. S is skew symmetric and D is symmetric, but they have denoted this part as S. So this is a wrong answer. But of course, D is the correct answer because they have clearly given S is symmetric matrix and D is a skew symmetric matrix. Clear? So shall we go for the next problem? Shall we go for the next part? Is that clear to all of you till this moment? Good. So let's go for the next part. A 2014 question from ECE Electronics. So please try to solve this. From matrices of same dimensions M, N and a scalar C, which one of the following properties does not always hold? Does not always hold. Any guess from your side? Option D, correct, because you have clearly seen fine. So you have clearly seen whenever you are transposing the matrix even number of times, then definitely the same matrix gets repeated. So this is always true. Next, just now we have seen any scalar multiplication of a matrix, if you apply the whole transpose, then definitely this is always correct. Similarly, if you have summation of two matrices and if you apply the whole transpose, then this result is also correct. But this result we can't assure until and unless the matrices are given, correct? So definitely here this matrix or Mn is equal to Nm and all these things, we can't need not be equal always, need not be true for all M comma N. Okay, so this option D we are not sure because we know matrix multiplication need not be commutative. So definitely D is the option which does not always hold. Okay, so this is a good question again, because generally people by looking at the options they feel first option is the correct answer and they will take that. Okay, so please don't overread the questions and don't lose marks in GATE examination. Okay, next, this is one good question from 2014 instrumentation. So please try to solve this. A scalar valued function defined as f of x is equal to x transpose A times of x plus B transpose x plus C, where A is a symmetric positive definite matrix. So A is symmetric. Okay, so A is equal to A transpose. This is what they have given, and with the dimensions n by n. Okay, so the dimensions of this A is n by n. B and x are vectors of dimensions n by 1. Okay, so this B has a size of n by 1 and this x is also of size n by 1. Okay, and of course C is a scalar. Then the minimum value of f of x will occur when x is equal to, the minimum value of f of x will occur when x equals. I put this question here because all of you know that if you multiply a matrix with its inverse, this should be I. Okay, in yesterday's class you yourself told me that you know this point, so definitely you can solve this question. Why it's D? Because Nagasai and Umesh, both of you told it's D. So tell me why it should be D. All of you. So please try to respond because this is a very good question. So please try to solve. Okay. Fine. Look, okay, you told D for last question. Okay, good. I couldn't understand the question. Okay, let me first make you to understand the question. I'll help you out. Look, see carefully. I'll tell you what's the question. See carefully. F of x is equal to x transpose. Given clearly that x is an n by 1 vector. Correct? See, in the statement it was mentioned b and x are vectors of dimension n by 1. If they are of n by 1, that means they have n rows but only a single column. So that means we have something like this. This is a n by 1 matrix. So can you tell me what could be the order of this x transpose? Look, forget about the solution of this question. Please try to answer my question step by step. If x is of order n by 1, can you all tell me what could be the order of this x transpose? Any one of you? The order of the matrix x transpose is how much? It's 1 by n, correct? So x transpose and the order here is 1 by n, okay, times. Next, again you have matrix A. Matrix A is of order n by n, it's clearly given, and of course you have a product of x here, x which is of order n by 1. So now if you multiply these three matrices, can you tell me what is the order of the resultant matrix? Any one of you? Suppose if you are multiplying these three matrices, now can anyone tell me what could be the order of this matrix? It's a 1 by 1 means, can you all agree if I multiply these three matrices, I will be getting some scalar. Will you all agree with me on this point? If I multiply these three matrices, I will be getting a scalar, correct? Next, b is of size n by 1 and also x is of size n by 1, okay. Oh, I mean the capital X, yeah, this is of size n by 1. Now plus b transpose, look, we are writing b transpose. So if b is of size n by 1, can you tell me what is the size of this b transpose again? All of you, can you all tell me what's the size of this b transpose? It's again 1 by n times x. This x is of size n by 1. So definitely when you multiply these two terms, again you will be getting a scalar. It's a 1 by 1 matrix. Plus you have of course a scalar c which is of order 1 by 1, correct? Because any scalar is nothing but a single row single column matrix. So definitely this is what you can have, which means, can you feel that this f of x is a scalar? Because this is summation of a 1 by 1 matrix which is nothing but a scalar plus some other scalar plus one more scalar. So can you all clear, is that clear to all of you that the summation, this total summation is the scalar, means f of x is some function in terms of x. Now we have something for f of x. Now the thing is, we want the value of x where this f of x will be minimum. That's the question. Look, now let us try to solve this. Normally if you generalize the things, they get a bit complicated. So let us take a simple example for n is equal to 2. If you take n is equal to 2, let us assume a is equal to a b and of course b c, because let us take the value of n is equal to 2. So that's why you can see they have given in the question A is a symmetric matrix. So definitely this is what the generalized expression we can take for A. Okay. Next, B they have given as n by 1 matrix. So here it should be of 2 by 1. So let us suppose something, you can take anything. Let us suppose alpha beta, not an issue. Okay. Next, C is a scalar anyhow, so no issue, and of course x is also a 2 by 1 vector. So if this is 2 by 1, let us take this value as x1 x2. Okay, because I am discussing the case of n is equal to 2. So this is how you can frame three matrices without violating anything in the question. A should be a symmetric matrix of order 2 by 2 of order n by n. So since you have taken n is equal to 2, we have framed a 2 by 2 matrix. Similarly, this B is of n by 1. So we have 2 rows and a single column. Same is the case with x, because here x is a variable. So we didn't put any fixed elements here. Okay, because we want to find what's the maximum, what's the value of x at which this function f of x is maximum. I think minimum they have given you. Yeah, minimum. Okay. Now, if you work out this procedure, f of x is equal to, look, x transpose, which is x1 x2 into A which is AB BC times again x1 x2. This is what you have. Next, look here, please don't misunderstand this. This is a capital X, okay. This here is a capital X because we are talking something about that matrix, okay. So see here, plus B transpose, which is alpha beta into x, x1 x2 plus some constant C. Correct? Can you all agree with me? If these are the cases for this matrix, then this is the expression whenever you take n is equal to 2 and by defining this as the matrices A, B and X respectively. Yes or no? So please try to respond. Can you all understand that this is the total expression when of this capital, this f of capital X whenever these three matrices are of this form? We have taken X transpose into A into X plus B transpose into X plus constant. Correct? Now, if you try to calculate the result of this, f of x is equal to, see carefully. Now, you know matrix multiplication is associative, so you can multiply in any format. Let us suppose I am multiplying in the first two matrices as this. So this is of order 1 by 2 and this is of order 1 by 2. So we will be getting again a matrix of order 1 by 2. So Ax1 plus Bx2 is the first element, and of course Bx1 plus Cx2 is the second element. So to this we have the multiplication of x1 x2 plus here this is of order 1 by 2 and this is of order 2 by 1. So if you multiply these things, we have alpha x1 plus beta x2 plus constant. Correct? And if you multiply these two matrices again, we have f of x is equal to, now if you multiply these two matrices, we have Ax1 plus Bx2 into x1, which is Ax1 square plus Bx2 square. Oh sorry, this is again multiplied with x1. So Ax1 into x1 means this total term Ax1 plus Bx2 into x1. So this will give you Bx1 x2. Correct? Plus again the matrix multiplication of these two elements is also Bx1 x2 plus Cx2 square. This is what you have. Correct? So can you all agree with me? Yeah. Let us change this as some other element D, because there is a possibility you will be getting confused with this C and C here. Okay. So let me write this as D. So now Bx1 Ax1 square. So this should be D here, and of course now if you try to calculate the things again, this should be D here. Okay. I am just changing because there is a chance you may get confused with this C and the C that we wrote here. Okay. So if that's clear to you, plus alpha x1 plus beta x2 plus constant. Now this is total f of x. Correct? Now this complete term is a scalar here, and this term is also a scalar, and C is also a scalar. So now if you calculate what is f of x, you will be getting Ax1 square plus b times of x1 x2, okay, 2b times of x1 x2 plus dx2 square plus alpha x1 plus beta x2 plus c. So this is the total expression that we have for f of x. Okay, this is the total expression that's available for f of x. Okay, so now this is the f of x, and you want the point of this x where you are having minimum for this function. Minimum for this function. Okay, now try to tell me one thing. This f of capital X, because this capital X is a matrix and it involves two variables x1 and x2. So this is a it's an expression that contains two independent variables. Correct? So if you write f of x is equal to Ax1 square plus 2b x1 x2 plus dx2 square plus alpha x1 plus beta x2 plus constant. This is what we have. Correct? So now you want the minimum term. Yeah, correct. So now you want the minimum value of this expression. So it's clear that we have two independent variables. So if you treat this as f of capital X, yeah, of course, but this is the best way to solve this. Okay, because otherwise you need to know many other things. Correct? So if you equate these two things to 0, because you know whenever you want the minimum value of this function or any maximum value of this function, then it's obvious, since it has two independent variables, you will be differentiating them with respect to those variables partially and equating to 0. So if you do this, we will be having 2ax1 plus 2bx2 plus, anyhow partial differentiation of this term, it's 0, plus alpha is equal to 0. This is what you have. Correct? Next, if you solve with respect to x2, we have 2bx1 plus 2dx2 plus beta is equal to 0. Yes, of course it takes more than 3 minutes, definitely I understand, but of course one thing is very clear, out of the 65 questions there will be at least some 40 questions where they can be solved within less than 2 minutes. Okay, so that's why they have given this. Now if you try to solve these two equations, please try to solve this. 2ax1 plus 2bx2 is equal to minus alpha, and of course 2bx1 plus 2dx2 is equal to minus beta. Now can we write this in matrix form as 2 times of a b b d x1 x2 is equal to minus alpha minus beta? Can we write this from these equations? Because if you multiply the terms, you will be getting the same equations again. So can we formulate these equations in this matrix? Yes or no? So please respond. Can you all formulate this matrix, these given equations, these two equations basically into this matrix? So now if you compare the things, we have 2 times of this matrix is nothing but capital A and this matrix is nothing but capital X is equal to minus B. This is what you have. So Ax is equal to minus B by 2. So definitely if you want this X, this is nothing but minus of, if you multiply with A inverse on both the sides, so A inverse B by 2. This is what you will be having. Okay. So X is equal to minus of A inverse B by 2, which is given in option C. Okay. Because when you take 1 by 1, you know you can take a 1 by 1 matrix and all, but of course conditions won't be that clear. Okay. So in exams always, if something, some property, if you have any confusion like this, you can always go for 2 by 2 matrix, okay, for simplification. Fine. So shall we go for next question? Did you all understand how can we formulate these two equations as this matrix? Okay. Look, now people are telling it's very lengthy, but of course if you see carefully, first of all, to understand this is a scalar, it will take hardly 1 minute. Okay, because you know this order, so if you multiply, you will know that it's a scalar. So here till this point will take 1 minute. Okay, next, to multiply these two matrices and to write these 3 steps, let us suppose you take 1 more minute. Okay, next, once you get this expression, you know you won't be writing all this story in the exam. Correct? Once you know this, you will be writing these two equations. Correct? So these two will take 1 more minute, and if you know these two equations can be written in this form, it takes some 30 seconds at maximum. So total, this is the time hardly needed to solve this question. And I told you, any question in GATE exam, if you feel it's tough, definitely it should be solved in less than 4 minutes and you could solve this in exam. Okay. Fine. Is that clear to all of you? Because it's generally a matrix function, so that's why it appears a bit complicated, but actually if you see, all the operations involved in solving this question are very simple to analyze. Okay. Fine. So please try to solve this question. It's a question from GATE 2016 again. So please try to solve this question. Look carefully. See the question carefully and try to answer this. A sequence x of n is specified by this matrix condition. So xn and xn minus 1 are given. So definitely when you know xn minus 1, you could get what is xn from these equations. For n greater than or equal to 2. So this is defined only when n is greater than or equal to 2, correct? And the initial conditions are x of 0 is equal to 1 and x of 1 is also 1 and xn is equal to 0 for all n less than 0. Of course, there doesn't exist any value of this series for negative integers n less than 0. The value of x of 12 is dash. So please try to calculate this and tell me the answer. You are given x0 and you are given x1. So if you know x0 and x1, by putting n value as 2, you can get x of 2 is equal to x of 1 is equal to 1110 whole square into 10 column vector. So if you calculate, you will be getting what is x2 and all. Okay. Look, let me do this question. So if you put n is equal to 2, you will be having x of 2, x of 1. This matrix is equal to 1110 square times of 10, and you know this value is already, x of 1 is given, this value is already 1. Now find x2 from this and tell me what's the value of x2. If you do it correctly, you should get x2 as 2. Please try to calculate this and tell me whether the value of this x2 is 2 or not. Okay, fine. Is the value of x2 is 2? Are you all getting this value of x2 as 2? Just try to square the matrices. You know, calculation of square of this matrix is very simple. So that's not an issue, correct? So you got x2 as 2. Now if you put n is equal to 3, x of 3, x of 2 is equal to 1110 whole cube times 10. This if you solve, you will be getting x3 as 3. Okay. You know this? First of all, before continuing the multiplication of matrix X, tell me one thing. Have you seen this matrix anyway in your first year undergraduation? Have you seen this kind of matrix anyway in your first year of undergraduation? Most probably in computer, you know, C language and numerical methods course. Have you seen this anyway in your C programming or C programming classes? They will be asking you to write a code for one very famous series which is called the Fibonacci series. Do you remember this name at least? Yeah, Fibonacci series. I think one more B should also be there. Fibonacci series, correct? Have you heard this name anytime in your first year of undergraduation? During C programming? Yeah, I think, but even civil engineering students will have some programming language in the first semester, correct? Yeah, name you heard. Okay, what's this Fibonacci series is? Look, initially you will be taking the two terms as x0 is equal to 1 and x1 is equal to 1. Okay, next, x2 is summation of 1 plus 1, 2. x3 is again summation of x2 and x1, which is 2 plus 1, 3. x4 is again summation of x3 and x2, which is 5. So generally if you take any term, xn is same as xn minus 1 plus xn minus 2. And of course you can't have negative terms here, means you can have at maximum 0th term, but not like minus 1th term, minus 2nd term and all. So they have defined x of 0 is 1 and x of 1 is 2. So if you put n is equal to 2 in this series, definitely you will be getting x of 2 is equal to 2, x of 3 is equal to 3, x of 4 is equal to 5 and all. And of course this is a Fibonacci series, and if you try to write the things, you will be getting 1, 1. These two are defined, predefined, correct? So now if you sum up these two things, 1 plus 1 will give you 2 as the third term. Next, 1 plus 2 will give you 3, 2 plus 3 is 5, 8, 13, next 21, 13 plus 21 it's 34, next 21 plus 34 it's 55, correct? I hope my calculations are correct. So 34 plus 55 is again 89, then 55 plus 89, 55 and 89 if you add, you will be getting 144, So 144 plus 89 is almost 233, and all this is a Fibonacci series, and this is generally the generalized matrix notation for the Fibonacci series. Okay, so that's why. But generally, if you don't know that point, you need to calculate things like this till you attain this 12 here. Okay. Okay. So this notation of matrix is general notation for Fibonacci series. And most probably I feel this question could have come for computer science or someone. Okay. Because branch was not mentioned in that year, so I am feeling that. Is that clear to all of you till this moment? So can you all understand this till this moment? This is generalized expansion for the Fibonacci series, and of course these matrices, when you simplify the things and all, you will be getting some generalized expansion with this as the normal general equation for that. Okay. So if you are clear with this, we will go for new topics. Okay. Because these are the 8 questions that we found, and in yesterday's class we have solved some 15 questions. So total 23 questions we have solved on vector calculus. This linear algebra. Okay. Why x of 1 is equal to 2? It is 1, right? Look, if you want x of 2, put n is equal to 2. So this is x of 1 plus x of 0. Okay, and the value of this is 1, and this is also 1. So 1 plus 1, it's 2. Something like this. Okay. So 233 is the 12th term. Of course, in the Fibonacci series, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. What did they ask for? 12. Of course, because they have defined with a not here. So definitely x12 could be the 13th term in the series. Okay. MUBA, I don't know what's the full name, but is that correct? Can you all understand this? Okay. So now we'll go for some new topics now. Look, we have seen different types of matrices and different properties associated with their multiplication. I wrote x of 1 is equal to 2. Where? Okay, sorry, I think I have misread this. This is 1 actually. Correct. Okay, yeah, I have misread on that, but actually it's 1. So 1 plus 1 is what? You will be getting the complete series. Okay, this is 1. Fine. Yeah, thank you. So now let us talk something on complex matrices as well. But of course, I won't be going into the more details of that, but generally we will like to see. Now, this complex matrices we have, as we have symmetric matrix and a skew symmetric matrix in real matrices. In complex matrices, we have few things like Hermitian matrix and a skew Hermitian matrix. Just I would like to make you know that there are few matrices here. So in Hermitian matrix, look, normally whenever you are talking about any particular matrix, let us suppose we are talking a simple case of 2 by 2, A, B, C, D, then it need not be possible that always these terms involved, means all these A, B, C, D are real numbers, correct? Sometimes there is a chance that one of them or maybe all of them can be a complex numbers, correct? So whenever you have some complex involvement in this, then we denote the complex conjugate matrix with a star, and this A star is nothing but, let us suppose, let me write one complex number here. See, we have already written. Okay, so B plus ID E minus IF. Let us suppose I have given you this matrix, a 2 by 2 matrix, where out of this matrix these two elements are complex numbers. Okay, so if you are having some complex entities within the matrix, then this complex conjugate matrix, or you can call this conjugate matrix, is denoted by A star, and this denotes the complex conjugates of the complex entities C E minus IF. This is what you define A star, and since this matrix it involves the conjugates of the complex numbers in the actual matrix, this matrix is called as conjugate matrix, and few times we have in a Hermitian matrix A is equal to A star. Okay, now if you talk about skew Hermitian, again I just wanted to because Okay, this is plus, correct. Thank you. Skew Hermitian matrix, if you want to talk something about skew Hermitian matrix, then we have A is equal to minus A star. Okay, things are similar. And of course, as we have an orthogonal matrix there where A into A transpose is equal to I, here we call that as unitary matrix. Generally questions don't come from this, or even if they come, they involve some matrix multiplications and all, but just I want you to know the things. So we are writing A into A star will be equal to identity matrix. So these are three different kinds of matrices which can even involve some complex numbers in them. Okay, so of course there is nothing much importance for that right now, but of course I just want you to know that sometimes the elements in the matrix can also be a complex numbers. Okay, so now let's go for some important parts. Let us calculate what is the minor of a matrix, minor of an element in a matrix. In a matrix. Fine. So let us see what is minor of an element. Now let us suppose you have a matrix as A, B, C, D, E, F, G, H, I as this matrix. Now if I want to talk something about minor of A, means if A is the element here, and if I want to say what's the value of minor of A, for example, or else let me do one thing, since we are dealing in 3 by 3 matrix, let me generalize the things. A11, A12, A13, A21, A22, A23 and A31, A32 and A33. This is what we have, correct? It's a 3 by 3 matrix in general. Now if you want to know what is minor of this element A11, see how we should identify that. This element is A11, correct? So if you delete this column and this row from this matrix, you will be having a sub matrix, and that sub matrix is A22, A23, A32 and A31 and of course A33 of course, and the determinant of this matrix in general means if you calculate the value A22, A33 minus A23, A32, this value is nothing but minor of A11. Okay, yeah, A22, A33 minus A23 into A32. So like this, how many elements you have in total? In total, in a m by n matrix, total how many elements you will be having? In general, if a matrix is of order m by n, then please tell me total how many elements will be having in this product. I mean in the matrix, it's nothing but mn elements. So total, when there are 3 by 3 size, we total have 9 elements, of course, which means there exists 9 minors, correct? So total 9 minors will be having. Next, let us recall this as m1. Okay, m1. Similarly, if you write the minors of all other elements, you will be getting the minor matrix as m1 1. Let us call this as 1 1 because this m11 is the minor of this element a11. Okay, so m12, m13, m21, m22 and m23 and of course m31, m32 and m33. This is what we have. Okay, so if this is the matrix, now once if you know this minor matrix, let us try to calculate something called cofactor of a element. So cofactor of A11 or Aij in general is nothing but -1 whole power I plus j into mij. Okay, I hope you get the meaning. Can you all understand what is this cofactor of Aij? Defined by -1 whole power I plus j into mij. So we get the values of I and j from the matrix. Means, for example, if I am talking about the cofactor of this element A32, then I value is 3 and j value is 2, and of course you can write this cofactor of Aij as -1 whole power I plus j into m times of ij, which is nothing but minor of this element mij. So if you know how to find the cofactor, can you write this cofactor matrix as, and let us suppose you are denoting this cofactor matrix, I mean this cofactor with capital Aij. Okay, let us suppose you are denoting this with capital Aij. Now if you have this cofactor matrix as A11, A22, I'm extremely sorry, this is 12 and this is A13. Similarly, A21, A22, A23 and A31, A32 and of course A33. If this is the cofactor matrix, then there is one very important matrix which is called the adjoint matrix. Right? Adjoint matrix. This is denoted by adjoint of A. This is how we denote a adjoint matrix as cofactor matrix when transposed. So the transpose of the cofactor matrix is nothing but the adjoint matrix. So this is very important because this adjoint matrix is really important because this is what we calculate finally for calculating inverse of any given matrix when needed. Okay. So now whenever this is defined as adjoint A, now see carefully. Let me try to calculate A into adjoint A now. A times of adjoint of A. Look carefully. Can I write this matrix as this cofactor matrix? Can I write this as minor of this A11 is nothing but cofactor of the small element A11. Correct? This capital A11 is nothing but the cofactor of the element A11 in this matrix. Correct? Because whenever you are writing minor, if you put A11 here, then definitely here we will be putting A11, M11, and here depending on the calculations you will get a positive sign. Correct? So can I tell this capital A11 is nothing but the cofactor of the element small A11? Yes or no? So can you all understand? Whenever we are writing this capital A11, can I call this capital A11 a cofactor of the element small A11? So if I write this value is nothing but minus 1 whole power 1 plus 1 into M11. Similarly, minus 1 whole power 1 plus 2 into M12. Next, minus 1 whole power 1 plus 3 into M13. This is what you have. Correct? Next, minus 1 whole power 2 plus 1 into M21. Minus 1 whole power 2 plus 2 into M22. Next, minus 1 whole power 2 plus 3 into M23. Similarly, for the last row, you can write 3 plus 1 M31 whole power 3 plus 2 M32 and also minus 1 whole power 3 plus 3 M33. This is what you have. Correct? And of course, minus you know how to calculate for any 2 by 2 matrix and all. So now, if you can understand this, now if you write this cofactor matrix, of course we have the same things like minus 1 whole power 1 plus 1 is nothing but minus 1 whole square which is a plus 1, so M11. Next, here there comes a negative sign because this 1 plus 2 is odd, so we have minus M12. Correct? Next, this if you simplify again you will be getting M13. Next, here we have M21. Because I just want to show you one very important result, so that's why even if the writing is very big, I am writing the things. Okay, so I want to show you one very important result at this moment. M21 and of course we have M22 and minus M23, and I think there should come a minus sign here before this. Okay, so M31 minus M32 and of course M33. This is what we have. Correct? This is nothing but the cofactor matrix. So can we write the transpose of this cofactor matrix is adjoint matrix. So can we write this adjoint matrix as, first of all let us put only adjoint. Okay. So can we write adjoint of this matrix as transpose of the cofactor matrix which is M11, next minus M21, M31, next minus M12, M22 minus M32, next M13, minus M23 and of course M33. Now as per this definition which I gave you here, adjoint matrix is nothing but transpose of this cofactor matrix. Can you all agree that this adjoint is nothing but this matrix? This adjoint of A is nothing but this matrix. because I want to show you two important results after writing this. So that's why I'm asking you. So please tell me, can you all understand that this adjoint matrix is something like this, where this capital Mij denotes minor of a particular element, correct? So now see carefully. Let us try to calculate one very important product in matrices, A times of adjoint of A. This is really important for us. Okay, A times of adjoint of A. So this is equal to A matrix. We have it as, I thought of doing it with 2 by 2, but since you are showing a bit interest, I thought of going for 3 by 3. A23, A31, A32 and A33. And when you multiply this with, now, yeah, see here. Now this is the adjoint A. So now M11 minus M21, M31 minus M12, M22 minus M32. Similarly, M13 minus M23, M33. Correct? Is this what we have? Is A into adjoint A nothing but the product of these two matrices? Can you all understand this? Can you all understand that A into adjoint A is nothing but these two matrices? Product of these two matrices? Now, here is the important thing. So please try to look here. This implies A into adjoint of A. If you calculate, look, this element, let me change the color. Look, this element is nothing but the cofactor of this element, correct? Similarly, this element is nothing but the cofactor of this element. Next, this element is nothing but the cofactor of this element, correct? So if you want the first column element in this matrix, see carefully. If you want the first column element in this matrix, then you need to multiply this row with this column, correct? If you multiply this, we have the summation of product of elements of a row of a matrix with their corresponding cofactors. Can you tell me what could be this? The summation of product of elements of a row of a matrix with their corresponding cofactors. See, you have this M11 as a cofactor of this A11, minus M12 is cofactor of this A12, M13 is nothing but cofactor of this small element A13, element small A13. Now, can you answer me? The summation of product of elements of a row of a matrix with its corresponding cofactors is nothing but determinant of the matrix, correct? We have seen this definition. So this is det A. Now if you want this first row second column element, multiply this first row with the cofactors of second row, that gives you a 0, and here also we will be getting a 0. Similarly, if you multiply the second row with the cofactors of first row, you will be getting again a 0. Here you will be getting a det A, and here again 0. So 0, 0 and det A. This is what you have, which means from this complete matrix you can take a det A, a scalar common, and you have an identity matrix 1 0 0 0 1 0 0 0 1, and this implies we have a very important result. A into adjoint A is equal to det A into I, and this result is really important for us. Okay, and the definition of determinant is nothing but the summation of product of elements of a matrix, elements of a row of a matrix with its corresponding cofactors, or you can take column as well, so it does not matter. So the summation of product of elements of a row or column of a matrix with its corresponding cofactors. Look, I will show you how this is det A and this is 0. Means generally when you multiply the summation of elements of a row with its corresponding cofactors, you will be getting the determinant of the matrix, and whenever you are multiplying any row with cofactors of other row, then you will be getting 0. I will show you for these two elements, and you can understand similarly for other rest of the elements. Okay, so whenever you are multiplying the first row with the first column, look what we will be having. Normally if you calculate the determinant of this, if you calculate this determinant A31, A32 and A33, if this is the determinant, can you tell me what is the value of this? Of course, you need not type everything, but I'll write, please tell me whether it's correct or wrong. Okay, so A11 into A22 A33 minus A23 A32, correct, minus A12 into A21 A33 minus A31 A23. Next we have A13 into A21 A32 minus A31 A22. This is what we have, correct. Is this the determinant of this matrix, of this 3 by 3 matrix here? All of you, so please try to respond. Is this the determinant of this matrix? Now, how you got this expansion? Normally we know if there is a 3 by 3 determinant, we were taught that this is the way how we need to calculate this determinant of this matrix. But why we are doing this formula? Why we are writing this formula? Let us try to see. Look, if you multiply the elements of a row with their corresponding cofactors, look, we will be having something like, I am calculating first element of first row first column element of first row first column element of A into adjoint A, because since you're at many points in your life you came to know that a 3 by 3 determinant should be calculated in this way, but we will see why we are doing this. Okay, so please see here, if you want the first row first column element of A into adjoint A, this is nothing but the matrix multiplication of A11 A12 A13 with M11 minus M21 and minus M31. I think there is no minus here. Okay, fine, correct. Is this multiplication will give you the first row first column element of this A into adjoint A? Yes or no? So please respond, correct, because the first column here is M11 minus M12 M13. Acha, here this is not like this, M21, okay, M12 and M13, correct. This is what we have. Now if you multiply these two things, look carefully what we are getting, A11 into M11. What is M11 here? The minor of the first element M11 we have calculated here. See, minor of A11 which is M11 given by A22 into A33 minus A23 into A32. So A22 A33 minus A32 into A32, this is what we have, correct, plus multiplication of this element with this with minus M12, so A12 into minus M12, this is what you have. And what is M12? So definitely if you write this matrix, A11 A12 A13 A21 A22 A23 and of course A31 A32 and A33. This is the matrix. So now if you are trying to write the minor of element 1 2, then this is the element which is lying in the first row and second column. Thank you Sridevi. A23, okay, fine. So if you delete these two, then we have this value of M12 as, of course this minus sign retains, and we have the value of M12 as A21 A33 minus A31 A23. This is what we have, correct, plus A13 into M13. So A13 into M13 is nothing but the minor of this element. So if you delete these two, you have A21 A32 minus A31 A22. Okay, I just want to show you because many a times in your life, whenever you are asked to calculate a 3 by 3 determinant, you are simply applying some formula. But today we will see why we are writing that formula always. Okay, so this is equal to, look, A11 into A22 A33 minus A32 A23. This is what you have. Correct? This minus sign we are taking it out. So minus A12 into A21 A33 minus A31 A23. This is what you have. Plus of course again A13 into A21 A32 minus A31 A22. This is nothing but determinant of A. Okay. Normally they will ask you put a plus here and put a minus here, and why this minus is coming here? Because of the cofactor, because minus 1 whole power 1 plus 2 will give you a minus 1. So that's why they are putting a minus here. Okay, it's not like, see, whenever you are putting a plus and a minus and again a plus, you should think why this plus and minus signs are coming alternatively. This plus and minus signs are coming alternatively because we are talking something about the definition of cofactor of a element. Okay, so is that clear? Now did you all understand why this is the way we are calculating 3 by 3 determinant of any matrix? Why this is the only way we are calculating? Clear? Can you all understand why we are putting this formula every time whenever we are asked to calculate determinant value? Okay, this plus sign, then put a minus again, then put a plus again. This plus and alternative, alternative placement of plus and minus is because we are dealing with the definition of cofactors, and in cofactors they give you an alternative plus and minus. Okay, so that's why, that's the reason. Okay, so now if you know this, this is what it happens. Now why this element should be 0? Whenever you are multiplying elements of any row with cofactors of other row, then why it should be 0? I will take an example of 2 by 2 matrix and I will help you. See here. In simple case, if this is the matrix, then see carefully, minus and minor matrix is nothing but, if this is capital A, minor matrix is nothing but, look, if you want the minor of A11, you will be deleting this column and this row, so A22. Next, if you want the minor of this element A12, you will be deleting this column and the first row, so A21. Next, if you want the minor of this A21, if you delete this column and row, you will be having A12, and similarly here A11. This is the minor matrix. Now, if you want the cofactor matrix, then the cofactor matrix is nothing but minus 1 whole power 1 plus 1, which is A22 minus A21, and of course minus A12 and A11. This is the cofactor matrix. Correct? So now if you find the adjoint matrix, adjoint of A is nothing but the transpose of this matrix. So A22 minus A12, and of course minus A21 and of course A11. This is what you have. So this is the adjoint matrix. So if you multiply this A times of adjoint A, here we are getting something like A11, A12, A21, A22, and of course this cofactor adjoint matrix A22 minus A21 or 12 minus A21 A11. This is what you have. So if you multiply these two matrices, look carefully now. This process is common for both 3 by 3 and 2 by 2, correct? But I have thought of showing you some result for 3 by 3 matrix, so I have given you that. But normally if you want to see, when you multiply elements of a row, with their corresponding cofactors, let us multiply. You will be getting A11, A22 plus A12 into minus A21. This is what you have as the first row first column element, and of course this is nothing but the determinant of this matrix, correct? You know, this A11, A22 minus A12, A21 is nothing but the determinant of this matrix. So that's why whenever you are multiplying any elements of a row or column with their corresponding cofactors, you will be getting a determinant value. Clear? Next, if you multiply the elements of a row with cofactors of other row, means if you are multiplying these elements with this, these are cofactors of this second row, correct? So if you are multiplying the elements of a row with cofactors of other row, you will be getting 0. If you want, you can check A11 into minus A12, A11 into minus A12 plus A12 into A11. Can you all feel this summation is nothing but 0 because they both get cancelled? Yes? Can you all understand this? All of you. Similarly, if you multiply the second row elements with the first row cofactors, let us see what happens. A21 into A22 plus A22 into minus A21, and you can see these things again gets cancelled because these are second row elements and these are cofactors of first row. So in general, if you multiply, means if you take the summation of multiplication of these elements of a row with the corresponding cofactors, you will be getting the determinant. But if you multiply the elements of a row with cofactors of some other row, definitely you will be getting a 0. That's why we have, and of course here you will be getting again, let me write the simpler case. Here you will be getting again one more dot A. Okay, so this is what you can have, and this is similar in this case also. Okay, this is how you will be getting, because for the first row first column element, since you are multiplying the first row with the corresponding cofactors, you will be getting determinant of A. But for calculation of other elements in the first row, you will be multiplying the first row with cofactors of second row and third row. So that's why you will be getting 0 in these two places. Similarly, for the second row evaluation, it comes only det A here, but not at these two places. And similarly for the third row, you will be having a det A at this point, but not at these two places. So this result has to be noted. Okay. So A into adjoint A is equal to det A into I. This is what we feel from this particular things. Okay. So if that's clear, I just gave you this. Next. So see here. So one thing is very clear, A times of adjoint A is equal to det A into I. Fine. Look carefully. Now, if let us suppose A inverse exists for this matrix, okay, for this matrix A, let us suppose A inverse exists. Now, if you multiply these matrices with A inverse adjoint of A is equal to det A is a scalar, so no issue, into A inverse into I. Since this is an identity matrix, it's not any trouble if you multiply this A inverse to the left or to the right. But actually, if suppose if you have B is equal to C, then if you are multiplying your A here, it's mandatory that you should multiply your A here on this right hand side, because you know this AC and CA may or may not be equal, so we are not sure. So definitely, as in real calculus, we have a flexibility of multiplying in any order, but in matrices we should be very much sure about the order of multiplication. So if you are multiplying this A here, definitely you should multiply it here. Okay. So if that's known to you, we'll move further things here. Look, this A inverse into A matrix multiplication is associative, so definitely I can multiply these two matrices first. So can you tell me what could be this value of A inverse into A? Any one of you? Can you tell me what could be the value of this A inverse into A? That's nothing but identity matrix, correct? So I times of adjoint A is equal to det A into, and again you know multiplication of any matrix with identity matrix will give you the same matrix. So this is A inverse. So you know this result, if you follow here, this is adjoint A and this is equal to det A into I, det A into A inverse. So which means A inverse should be equal to adjoint of A divided by det A, correct? And this is why you are calculating, you are applying this formula adjoint A by det A to calculate the inverse because of this equation. Okay. So if A inverse is equal to adjoint A by det A, now one thing it's very clear from this equation, for A inverse to exist, can you tell me what's the condition? By looking this fraction, you know this is a fraction, correct? And in the denominator you are having a scalar. So if this want to be some finite thing, what should be this det A? This det A, can you tell something about this det A? If this fraction want to be existing, this det A should not be 0, correct? So for det A to exist, det A should not be 0, and we call this as A is non-singular. Okay, singularity means its determinant is 0, but here we will be calling this as this determinant of A. I feel like I have written something here, so A is non-singular. Now can you all understand, whenever if A inverse has to be existing, this determinant of A should not be 0. Why we are writing this condition so many times? Because A inverse is given by this particular formulation adjoint A by det A, and whenever you want to have some finiteness for this det A has to be non-zero. Okay, and this condition has been asked many times in GATE examination, of course. Okay, so in your schooling and in your +2 and all, you are having these results with you, that's it, but you don't know why these are happening. Okay, but today I think many of you learned why all these things are happening, why a 3 by 3 determinant should be calculated in that way, why a 2 by 2 determinant should be calculated in a particular way, and why for the existence of inverse determinant should not be equal to 0 and all these things. Okay, fine. So can we go for the next part? Can we go for the next part now? Okay. Okay, so see here. Now one thing is very clear, for A inverse to exist, this is how it should happen. Next, we have A times of adjoint A is equal to det A into I, correct? Using this result, let us suppose, can I calculate the formula for adjoint of adjoint A in terms of difference between radian and degree, how to use in gate calculator. I have taught many times, but okay, in today's class also I'll be taking that, how to enter degrees and how to enter radians. Okay, so not an issue. So can you tell me something in terms of A and that A here? Look, I gave you this hint. We know this formulation, A into adjoint of A is nothing but that A into I. So if this is the case, so please try to tell me what could be the value of adjoint A in terms of A and that A. Okay, and if you want, I could give you one property. Determinant of k times of A, whenever this A is an n by n matrix, is nothing but k power n into that A. Anyhow, in tomorrow's class we dedicate the complete class for determinants, so we will see what are different properties of determinants and all. So we will see that. That A whole power n minus 2 into A, that is what you are telling, Divya. Any other answers? That A whole power n minus 2 into A. Okay, any other answers from your side? That A whole power n minus 1 whole square. Okay, I am asking you for a matrix adjoint of adjoint A. Any others? You can use this formula anyhow. That A whole power n minus 1 whole square. One thing is very sure, look, please try to understand something. First of all, tell me, this adjoint of adjoint A is a matrix or it's a scalar? All of you. So first please try to tell me, this adjoint of adjoint A is a matrix or is it a scalar? It's a matrix. And if you are telling options like that A whole power n minus 1, that A whole power n minus 1 square, all these are scalars, correct? Yes? Can you understand this? This is a matrix, but the values which you are telling in the comments, these are scalars. Okay, so please try to do something to rectify this. Okay, so let me help you out. See, whenever we have A into adjoint A is equal to that A into I, can we write B into adjoint B is equal to that that B into I, that B into I. Can I write this for any square matrix B? Can I write this? B into adjoint B is equal to that B into I. Can I write this for any given square matrix? If I can write this, look, this implies B times of, okay, let us take one thing, B is equal to adjoint of A. Okay, so we here our intention is to find this matrix adjoint of adjoint A. Okay, next, to know this, first of all we should understand few things here. Adjoint A times adjoint of adjoint A is equal to that of adjoint A into that I, because you know, if there is two matrices, then definitely this is that adjoint A into, oh sorry, this is not that I, but of course, oh, yeah, here we have a I. Correct? Now see carefully. First of all, let us try to calculate what is this that of adjoint A. If you can understand what is this that of adjoint A, let us substitute that of adjoint A and let us multiply this with the inverse of adjoint A and we will be getting the matrix. So determinant of this adjoint A, how to calculate this? Look, we have A times of adjoint A is equal to that A into I, correct? So if you apply determinant on both sides for this, then that A into determinant of adjoint A is equal to this that A is a scalar and this scalar is a multiplication of this matrix I. So whenever you try to take this scalar out, you have that A whole power n minus 1, or sorry, n into determinant of I is nothing but 1. So this that A, if it is non-zero, then we can write that A whole power n minus 1. So this implies determinant of adjoint A is equal to det A whole power n minus 1. This is what we will be having. Okay. So determinant of this adjoint A is always det A whole power n minus 1. Next. So see here, we have adjoint A into adjoint of adjoint A is equal to, now determinant of adjoint A is nothing but det A whole power n minus 1 into I. This is what you have, correct? Sridhar, we are asking repeat left side equation. Look, let us suppose you have a matrix which is of the form Ka, okay, and this A is a n by n matrix. Now, if this A is a n by n matrix, can you tell me what could be the value of det of K times of A? Can I write this as K power n times into det A? Can I write it this way? Other side equation. Acha, left side, okay, fine. Means if this is the case, you are asking me, this is okay to you, and here asking me here, how this is det A into det of adjoint A, correct? Because if you have two matrices product A times of B, you can write this as det A into det B, okay. This is what you have all the time, so definitely you can write det of adjoint A is equal to det A whole power n minus 1. Is that clear to all of you? If that's clear, then we will go for the next part. Okay, fine. So is that clear? Is that clear to all of you till this moment? Okay, so now if you want this adjoint of adjoint A, then it's simple. Adjoint of adjoint A is nothing but det A whole power n minus 1 into the inverse of this matrix adjoint A. This is what you will be having finally. Yeah, this one maybe. So this is what you have, and of course you know the formula for adjoint is adjoint A is equal to A inverse into I into det A, of course. So you can substitute this adjoint of A here and you can calculate the inverse using that substitution. Okay. So if you substitute and all, since adjoint A is det of adjoint A is known to be det A whole power n minus 1 and all, you will be able to calculate what's the value of this. Because in tomorrow's class anyhow you will be coming to know AB whole inverse is nothing but B inverse into A inverse. So if you know that formula, then there is multiplication of two matrices A inverse into I. So you know how to calculate adjoint of A whole inverse, which is of course, if you calculate the determinant of the, if you want to find the inverse of that, this det A is a scalar. So if you pull this det A outside, you will be getting times A into I inverse is again I. So this is something you will be getting. So if you substitute this here, you will be getting some matrix here. So det A whole power n A det, okay, this is a matrix of order n, so definitely you will be getting one n here. So you can substitute this. So anyhow in tomorrow's class we will be seeing this in properties of determinants. Okay. So my main intention for you today is to tell you that this equation A into adjoint A will always give you det A into I. Okay, so this is the basic equation for having different properties of determinants. Okay, if you can understand this part, then that's clear for now. Okay, that's why I have given a 3 by 3 example to let you know how things gets happened. Is that clear to all of you till this point? A times of adjoint A is equal to det A into I. All of you. So please respond. Are you all clear till this point in today's class? A times of adjoint A is equal to det A into I. Okay, fine. If that's clear, then we'll stop this lecture today. We'll have a short lecture today because here we have finished the matrix algebra, and in tomorrow's class basically we focus on these two parts where we'll talk some properties of determinants and we'll see something called rank of a matrix in tomorrow's class. And this concept of rank is very important. Okay, please don't miss tomorrow's class, because this concept of rank here is really important. And determinants, of course, if you know some properties of determinants, we have seen different types of matrices, like basically symmetric matrix, skew symmetric matrix, orthogonal matrix, involutory, we have seen idempotent matrix and some other types of matrices. So if you see, we'll see each and every property of determinant for each and every kind of these matrices. Okay, so tomorrow's class, if you attend tomorrow's class, definitely many a times gate questions comes from this part, determinants or rank of a matrix. So please try to attend tomorrow's class. Okay, so that's what I want to tell you. And of course, anyhow, this is the Telegram group of engineering mathematics, where we will be posting all our questions, and you can respond and you can discuss few things here. So definitely, if you are here for the first time, please like the videos and share them among your circles, so that they will be of helpful to others as well. And since this content is for free, many of others will be getting benefit out of this. Okay, so here this is a group for Telegram. This is a group for engineering mathematics, and of course this is a Telegram group. So definitely please try to join this group, because we'll be posting all the notes of every class, and of course we'll be discussing some good questions which are posted by many of our friends in this. Please do check last equation. Muba, you are talking something about this equation. Are you asking me about this equation, MUBA? What is MUBA? You please. No. Then something here from this slide. Okay, previous. So where is the last equation? This equation. Are you talking about this equation? Left side. Yeah, this is the left side, of course. Yeah, right, left. Okay, this is the left side. Any issue with this equation? Adjoint of A inverse. Okay, something here. Look, let me tell you again, if you are having a bit doubt here. Look, we have A inverse is equal to adjoint A by det A. Correct? So this is nothing but adjoint A is equal to det A into A inverse. Correct? So now, of course, previously I have multiplied one I also, but of course multiplication of I doesn't even change the matrix or doesn't even change the determinant value. So because det A is 1 and all, so definitely if you want to calculate the inverse of this matrix, you need to apply inverse for this. Correct? And of course this det A is a scalar, so det A you can take this out, and this is something like this. Okay, because A inverse whole inverse is nothing but A. Fine. Is that clear? All of you, is that clear? No, see, determinant of A inverse is 1 by det A, but here we are not calculating the determinants. Okay, we are just calculating the matrices till that point. Are you all clear? Here we didn't apply the determinant. Okay, we are not calculating the determinant of this A inverse or something like that. We are just trying to calculate the inverse of this matrix. Is that clear to all of you, or any doubt at this moment? Okay, so there is no issue now. So anyhow, this is our Telegram group, so you can always join here, and if there is some doubts at any point on this lectures, you can put a screenshot of the video and you can ask something here. Definitely I'll be able to respond as soon as possible. And of course these are the official contacts of us. So here we have the website, so where you can visit this and you can get all the required information from this website. And of course we have 2 Telegram groups exclusively for mechanical on the right hand side, and the one onto the left hand side is for all others, ECEW and whatever is there. You can all join this channel. These 2 are channels, but of course this is a group. Okay, in this there can be two-way communication, means I can post few things and you too can post few things here. And of course here these 2 are channels, so whenever you want some required information, you will be getting it from these channels, because there is already a lot of content that's uploaded on these 2 channels. And of course these are the 2 official contact numbers of Engineers Hub. And of course, at your acknowledgement, we are conducting a scholarship test that is in progress now. So definitely if you would like to give an attempt, you could come to our office. We are situated in Visakhapatnam in Daba Gardens, and of course this scholarship test we have started it commencing on 6th of December, and that will be continued till 13th of December, which means only 3 days are left for closing of the test. And of course, of course we told you we are in Visakhapatnam, so if you would like to see us, you could definitely come to our office and we could guide you at our best. Okay, so is that clear to all of you? If there is some doubt at any point of any lectures in this course, you can always put a screenshot of that and you can ask me the same thing in this group here. Okay, is that clear to all of you? Is that clear to all of you? Okay, fine. So then that's for today's lecture. So we'll meet tomorrow sharp at 9 PM and we'll see some very good properties on determinants. Okay, for every matrix, for orthogonal, for involutive, for idempotent matrix and all these things, there are some special properties that of this determinant. So please don't miss tomorrow's class. If you attend tomorrow's class, you will be able to solve 50 to 60% of total previous year gate questions on matrices in very less time, maybe hardly less than 30 seconds for each and every question. Okay, so please don't miss tomorrow's class, because tomorrow's class is the crucial class for discussing all the properties of determinants and all. So that's from my side for today. Thank you all. Have a nice sleep. Good night. To attend scholarship test, do we need to be in Vizag? Yeah, because we are not conducting it online this time, so if it's better if you could come to our office and write that. Okay, and of course in the website you have a link for registering for the scholarship test. So as soon as you click this link, then it will get redirected for your form. So once you fill the form, our team will get into contact with you and they'll allot you some slot so that you can give the test in the same slot. Nayesh Chauhan, you're asking something? Okay, you haven't started mathematics yet? Okay. The best way at this moment, I am suggesting you, please don't start reading books like B.S. Gravel and Erwin Kovacic at this moment. Okay, because gate is very short. I mean, it's in very near time. So if you start reading the textbooks and all at this moment, they'll take a lot of time. Okay, so please don't go into some very detailed course books or something like that. Better solve all the previous gate questions in all the subjects if possible within these 2 months. Okay, because it's hardly today is 9th, and if 5th and 6th are the dates of first lot of exams, then definitely it's hardly some 55 days or something like that. So please don't go for some comprehensive materials at this time. Okay, so please try to solve previous year gate questions and try to learn how the different ways of solving the questions. Okay, that's what I can suggest you. Fine. Is that clear to all of you? So if that's clear, we'll take a break for tomorrow. Okay, thank you all. Have a nice time. Good night.